So today, which way do I go? Today we're going to continue our talk about instabilities. So I'm going to go through the two-fluid instability better because I was unhappy with how that unfolded yesterday or Tuesday. There will be a homework up tonight, so I'm going to post a homework today, and it'll be due next week. Okay. Does anybody have any other questions before I get started? Because I'm gonna jump headfirst into math. I'm really good with math.
Do you know?
Santiago first.
Oh, I was just going to ask, is this going to be one of the lengthier questions or lengthier homeworks?
Yes, this homework's gonna be long. So plan your weekend because it's.
I'll have to do this on the weekend because I'm going to be in Boston for a conference Monday through Thursday.
Yeah, do it this weekend.
I can always just do it while I'm there. So.
Sure, it's better if you do it over the weekend and then you can email me questions. Yeah, but it's going to be, so I don't remember exactly what's on this homework set because I haven't actually finished it yet. I need to go through it, sit down. But one of the homework problems is go through this derivation with surface tension. It's not super bad, but there's a lot of pieces to put together. And then you also have to keep this surface tension term. And you can see how surface tension suppresses Rayleigh-Taylor and Kelvin-Helmholtz. So that's it. It's heavy. It's not as bad as like your quantum or E&M homework, I don't think. But it will be longer. Okay, so let's set up the stage. Let's set up the stage over here. Is that in my picture? Yeah. So I have two fluids. I have a rho prime and a background velocity u prime on the top and a rho and a u on the bottom. And then we're going to perturb it in some way. And the perturbation height we're going to call xi. This is the height of the interface. And we're going to be incompressible. So div v equals 0. And irrotational, yeah.
Sorry, real quick. Do you
Okay.
know when next week that homework will be due?
Thursday.
Thursday.
I'm sorry, did you have another question?
That was the question.
Oh, that was your question. Sorry about that. I totally answered his question first. So it's incompressible and irrotational. And the second one lets us say that V equals minus grad phi. So these two imply this guy. So this is our basic setup. So we're going to do everything with it'll be a mix of phi and velocity because they have different representations and the different representations do different things. So the first thing that we need to do is lay out our main equation, which is Navier-Stokes again. We'll just use Euler. We'll throw out the viscosity this time, though that is an interesting question of what happens when you put the viscosity back in. So we start with d by dt of v plus v dot grad v equals minus grad p over rho. Rho came inside because incompressible. Minus grad capital phi, which I'm going to call g rho in a second, so I'll leave it as capital phi here. Oh, but I'm writing this down so that I remember. I said I was going to derive Poisson's equation. But I forgot. So the gradient of the gravitational potential, this is going to give you a g rho. So then we say that we invoke the incompressible conditions, and we call the velocity grad phi. And we use a vector identity that allows us to get rid of some terms. So this becomes minus d by dt of grad phi plus grad 1/2 v squared. Here I've pulled, so this is just plugging in the potential. Here I've pulled a vector identity and thrown a thing out because there's a thing that goes like the curl of v, which we get to throw out, plus this 1/2 v squared. So that just comes from a vector identity. Plus grad p over rho plus grad big phi equals 0. Yeah, okay. What's that?
Those are two separate files, right?
Yes.
Okay.
This little phi, that's an important question, thank you. This little phi is the potential, and this big phi is the gravitational potential. Grad big phi equals 4 pi g rho. So this is equivalent to saying, as an equivalent description of the gravitational force. Also, you've seen this in E&M as well, right? Oh, I'm sorry, del squared phi. What am I doing? Del squared phi. Del squared of the electric potential also gives you the charge inside. We'll go through that. I'm not going to go through that. So this is Poisson's equation, but we don't need that. So I'm going to now, so I've got a full derivative on every one of these, so I'm going to integrate. And I'm left with minus d by dt of phi plus 1/2 v squared plus plus p over rho plus, I'm going to replace phi with g times xi equals some constant of integration. Ready with that? I basically just get rid of all the grads. Because of that, you pick up a constant of integration because there is an integration that you do. And we replace phi with g xi. Okay, so we're going to need this in a second. Yeah.
So is the grad capital phi in the equation right above where you say everything equals 0, is that supposed to be squared?
No. It's squared here.
Squared there, but not in the equation.
Okay, sorry. Del squared phi is 4 pi g rho. This tells you how to find the gravitational potential. Grad phi is the gravitational acceleration, and this is a vector. This one is a scalar statement, and this is a vector statement. This is just how you find the gravitational potential. And this is equivalent to saying, so what you do is you say that F equals gm over r squared, and you got a minus sign there. And then you say that F equals minus grad phi, and you grad phi, and then you integrate and you turn this mass into a density, an integral over the density, and then this comes out. But what we need is just grad phi, which is just the acceleration. And here, so I've written it as little g. This could be a function of space if you have something complicated, but for us, we're going to assume our acceleration is a constant. Yeah.
So if that's the case, where does the xi come from?
Because grad phi is g is my acceleration, and when I integrate this in z, I get phi, this should be a capital phi equals g times z.
Gotcha. Okay.
Makes sense. Good question. Thanks for asking me all of the little questions that I skipped. Okay, put a pin in that for a second. Let's talk about the actual interface. dxc dt is equal to two things. I can say, so this is the velocity of the interface, of the top of the interface. And let's, throughout we're going to call this xc1 because the perturbation is small. We're going to perturb everything. Oh, actually, I need to perturb things first. So we're going to perturb things by saying that phi1, or phi, is going to equal minus u times x plus phi1. So my background flow, my background potential, velocity potential is just u times x, because my background potential is v, or is u. Sorry. My background velocity is u. And when I take a derivative of this with x, then I get the x component of the velocity, and I just get u. That makes sense? So this is the background solution plus my perturbation. And I'll have a similar one for the top, phi prime equals minus u prime x plus phi 1 prime. So now I can say that the the interface height is going to be dc1 dt. And now I can just expand this with the convective derivative. And that gives me partial c1 partial time plus u partial c1 partial x. Okay, let me do that better. This is going to be plus u plus v prime dc1 dx, because this is the actual velocity. But the v prime multiplied by the c1 prime is a second order term. So I'm linearizing it by throwing this out here. So we're just going to say the full derivative of time is dc1 dt plus u dc1 dx, where this is the now we've linearized here. We've thrown a term out. This also equals, because I know it's the velocity of the fluid at the top, minus d phi 1 dz. So I have this equation here, partial c1 partial t plus u partial c1 partial x equals minus d phi 1 dz. And I'll have a similar one. Let me erase my development work. I'll have a similar equation for the top part, dc1 dt plus u prime dc1 dx equals minus d phi 1 prime dz. So I have the same thing on the top and the bottom, because the interface is the interface at the top and it's the interface at the bottom. So we get a similar equation for the interface looking at it from the top solution or looking at it from the bottom solution. And the only difference is u1 and phi 1 prime. So now what I'm going to do is I'm going to assume that C1 is equal to some constant A times exp of minus I omega t plus kx. So this is just a wave. So the surface is going to go like a wave in some way. And then phi 1 is going to be equal to c, this is my other amplitude, of exp of minus I omega t plus, oops, I missed an I here, ikx, plus ikx plus kz. Not imaginary. Why not imaginary? Because this one doesn't extend to infinity. This one extends to nothing at infinity. So one of the boundary conditions that we have that we need to impose is that far away from the interface, nothing's happening. So I can't have an interface at the surface of the ocean. Like a wave on the surface of the ocean is not going to affect the upper atmosphere of the planet, right? So all of my perturbations have to go away at infinity, at z equals infinity. Yeah.
This is the a e to the whatever, that's just coming from the nature of the problem. That's not coming from any math stuff.
What?
It's not.
No, this is math stuff.
Okay.
So this is where what I'm actually doing is I'm replacing C1 and phi 1 with their Fourier transforms. And I'm rewriting the equation in this Fourier transform space, and then I can get rid of the integral because of everything on the inside has to be 0 too. So when I'm really doing the Fourier transform,
That's the stuff we did like a little bit.
yeah, so we did this a little bit ago. It's the same idea. So I have e to the ikx minus omega t. That's this thing here. And that's the same Fourier basis function that I'm going to use to describe my space. So the Fourier basis functions, I can take, so e to the ikx is just one basis function for Fourier space. I can describe any function that I want with some combination of Fourier modes. So I just need to talk about one of them, and then I can talk about all of them because I'm being general, and then I can talk about my actual full solution. Does that make sense?
Yeah.
So that's a good question. I'm glad you asked. So this isn't just pulling things out of my butt. This is because I'm linearizing things, everything works. What's it? You good?
Yes.
Okay. So C1 is the height. Phi 1 is the velocity in the bottom. And then we'll have a similar phi 1 prime equals C prime exp minus I omega t plus I k x and this one minus kz. The z behavior has to go to infinity or go to 0 at plus infinity too. So we have a minus kz here and a plus kz here. But other than that, so I'm calling everything Fourier modes, and then I'm applying the boundary condition that if I get far away from the boundary, the solution has to go to 0. So that's why we get ikx, but just a regular kz. Why are these k's the same? Because del squared little phi is also 0. Because of that, my kx and my kz are the same k. If that wasn't a question that you had, then don't worry about it, but I'll improve that later. So we have the same k, we have omega. So now we're gonna just drop these guys into these equations, and we're left with I times minus omega plus ku times a equals minus k times c, and then I times minus omega plus ku prime a equals plus kc prime. So, okay, what did I do? I talked about the hydrodynamics equations, but haven't used them. I talked about what the interface is doing in two different ways. I talked about it as the velocity, but then I also talked about its own full time derivative. And so we can relate those two things. Then we take our Fourier basis function, which is this. This is just a Fourier basis function. And plug it into these two guys, and then we're left with these two equations, which we'll need in a second. So the reason I want to go through all of this is so that you can see the process kind of as I would naturally do it. Yeah?
So just to make sure, C is just the distance from the interface or motion vertical?
C.
C is?
Yeah.
C.
C is the height of the water.
Okay.
So if you're like if you're standing in a pool, Z equals 0 is where the water cuts your belly, and then C is the distance from the distance up, where down. And this is the thing that we actually need to find, because this is what's going to do something amazing. But all I need to do is find out how omega and k are related, because that will tell me how C1 is related. C1 behaves. So we've taken what was a complicated differential equation and turned it into just exponents. Yeah.
Just to like we're kind of like guessing the solutions for the differential equations using
With this?
Yeah, this stuff.
You will see people tell you that, and that is not true. People will tell you, I'm just going to guess that this solution looks like this. It's way richer and way more complete than that. It's not a guess. It's, I get to use this because it all works together. Does that make sense? So it's more than just a guess. So you guys took, how many of you guys have taken linear algebra?
We've done it in math physics.
You've taken linear algebra and math physics, right? So if I talk about basis functions for a matrix, that's not going to be too weird, right? So when I have a matrix, I'm going to go on a little aside here. This matrix is equal to some amplitude times x hat plus some amplitude times y hat plus some amplitude times z hat. Or sorry, some vector. Say I got some vector v is some amplitude times x hat plus some amplitude times y hat plus some amplitude times z hat, right? So what are my basis vectors here? X hat, y hat, and z hat, right? Now I can rewrite this same vector in some other, let's call this, I'm not going to call it v prime because it's the same vector, but I can have some other basis vectors that I can put in here. A prime x hat prime plus b prime y hat prime plus c prime z hat prime, right? I can just use a different basis function to describe this vector because that basis function is easier. So one reason that I would do this, I just did this with a grad student recently because we have a cubic domain that is described by x, y, and z, but we want to make an image of it in this oblique direction here. So I need to rotate this into some x prime, y prime, z prime. And how do you do that? How do you find out the matrix that takes you from one basis to another? Assuming, sorry, buddy of mine just sent me a picture of his grandfather's mandolin. So I have this other axis. I want to describe the same thing with these new vectors. The transform matrix is just the unit vectors as column vectors. So the matrix to go from this set to this set is just the unit vectors. Because as long as the unit vectors are orthonormal. Does that make sense? So, so I know how to transform from these basis vectors to these basis vectors by this function. I'm going to do the same thing, except the inner product is now different. So we use the dot product a lot to do all this algebra, right? So that's called in general the inner product. And that's just a way to take two vectors, bring them together to get a scalar. What we're going to do now is we're going to write these, instead of vectors, now I have functions. And my function basis vectors can be whatever I like. But my function space also is described by basis vectors. So I can use x, y, and z, which I'm doing here. Or I could use omega and k, and I just have to change bases. So all I'm doing is changing bases. So I like your question. This is important because you will see people say, we're just going to guess a solution, but it's so much richer than that. What you're doing is saying, this is my basis function for my new system. I'm only going to deal with one of them, a single value of the amplitude, a single value of omega, and a single value of k. But I know that once I know how all these things are related to each other, I can build my whole complex real space solution by saying, here's my initial condition in Fourier space. It's going to evolve like this in each of the waves. And then I can boost back to real space. So it's a change of bases, like you did in vector in linear algebra. And what's that?
So I was just going to say, like, the reason we're doing Fourier right now is because we're dealing with waves, so that's just like the easiest, like.
No, we're dealing with Fourier now because Fourier makes everything easier. And waves come out of it. But really, the reason we're dealing with Fourier is because this d by dt turns into just multiplying by omega. So I've taken this equation and plugged this in. What really happened is I'm converting what this derivative does, because the derivative is relative to the basis, right? So if I change my basis functions, I have to change my operators too. So my operator goes from a time derivative to multiplying by omega. That's really the way we're doing it. But also, because in all of this process, you'll notice a couple of times I linearize things. That's really crucial for this to work. Because if we didn't linearize the shit out of everything, then this doesn't work anymore because my Fourier modes aren't all independent. Right now, my Fourier modes are all independent. I'll show you, actually, no, that's going to just be confusing. I'll show you what happens if you don't linearize things and still try to do the harmonic analysis. Maybe I'll do that when I'm done here. I'll finish this and then do. I'll do this again. I'll show you what Navier-Stokes looks like in Fourier space, both linearized and non-linearized. Okay. So these two equations now describe these two equations. This is now the interface described in the Fourier basis. Now I have my unknowns are A, C, and C prime. I have too many unknowns for my equations. I have two equations and three unknowns, so I need another equation. And that's where we'll use this now. So now we're going to use the fact that the pressure is constant at the interface. And if it wasn't, things would blow up, right? Bad things would happen. So we'll solve this for pressure. So we get P equals a rho goes over everything goes over to the other side, so I get a minus rho times minus d by dt of phi plus 1/2 v squared plus g times c1 plus rho f of t. And then I've got the same equation for the top side, rho prime minus d by dt of phi prime plus 1/2 u squared plus, or v squared, v prime squared plus g times c plus rho prime f of t. This, p equals this, or this equals this. These two things equal each other. So now I still have a square in here. Y'all see it, this v squared. So I need to get rid of that, because having a square means that it's not linear anymore. And this Fourier analysis breaks down if the equations aren't linear. Is that the next step? Okay, so we need to deal with this first. So let's first deal with this term. So we're going to have, so we'll put everything to the one side, and we'll have some term that looks like k equals rho f of t minus rho prime f of t prime. And that equals all of this on the other side. But if we say this needs to be true for, since this is not a function of x and it's not a function of my perturbation, this statement has to be true far away from the boundary or when the perturbation goes to 0. So if I throw out, if I throw out all of the small things, that's this guy, this guy, this guy, and this guy, and then the velocities just become u, kappa is just equal to 1/2 rho u squared minus 1/2 rho prime u prime squared. Okay. So this is just setting my constant of integration based on my boundary conditions. Right? So now I can say something about what that constant of integration has to be. It has to be these two guys. The other thing that I need to do is deal with this square term. So I've got v squared, and that's equal to u. Am I having a stroke? No. U x hat minus grad phi 1 squared. Does that make sense? So my velocity is just my velocity squared is just my background plus my perturbation. In velocity space, my perturbation is minus grad phi 1. I square that. So when I square this, I get u squared minus 2u d phi 1 dx plus grad phi 1 squared. What do I get to do to this equation to make it simpler? Linearize it. How do I do that?
Everything squared.
Get rid of everything squared. So who's squared? This one can stay. This is a constant. This is something that I know. I already know how to deal with u. It's the phi 1 prime, or it's the phi 1 that I don't know how to deal with. So the squares go on the phi 1. You don't have to throw out everything that has a square on it. Just every time you have two tiny things. So every time your perturbation shows up twice, throw that out. Okay, so this v squared turns into this simpler equation, just u squared minus u d phi 1. And then there's a similar one for prime. So I take this, I plug it into here. I take all of these dt's, and what do I replace dt by? What? Almost. Minus I omega. Because it's a minus I omega that goes in front of the t. But yes, omega, that's the important part. So we get some minus I omegas. What are, I got some k's over here. They will show up.
Wait,
so,
can I ask something?
yeah.
I thought, so you have phi, like little phi, equals negative ux plus phi 1. I thought like phi 1 was a constant.
No, phi 1 is my perturbation. This is my tiny thing.
Oh.
U is my constant.
Okay.
It's my background.
Alright.
Okay, so yeah.
Could you quickly explain how you got k is equal to like?
This thing?
Yeah, that thing.
Yeah, so I subtract these two equations. So these two things equal 0. And then k is the difference of these two things. So there's a minus sign on all of these. Right? So there's a minus sign on all of those. And then I say, well, this has to be true far away from the perturbation, far away from the interface perturbation. So if I set all of my 1s to 0, so all my tiny things, my phi1 and my c1, if I set those both equal to 0, then this stuff here, which I'm just going to call k, is equal to just 1/2 u squared, just this term and just this term. Because these are the only two terms that survive if I turn the perturbation all the way down. So you just turn the perturbation all the way down, you can throw out this term and this term, and then you're left with just these two terms just become 1/2 rho, the difference of the kinetic energies. Okay, so now we plug this into here, and we get that, let's just write it out, rho times minus dt of phi1 minus u dx phi1 plus g c1 equals rho prime minus d by dt of phi1 prime minus u prime d by dx of phi1 prime plus g c1 prime. No, not prime. C1 is C1. C1 is the same for both. Both coming up and going down, see the same C1. So here I've used this to get rid of the constant of integration. I've used this to make this center term not square anymore. So now this is linear in phi1. Otherwise it would have been square in phi1, and that's a problem. So then I replace all my I omegas, and then I've got a statement that has I'll just write it out. So I replace all these things with I omega and k, and I'm left with rho times,
Dr. Collins?
yeah,
Where did the u squared go?
which one?
So in the v squared substitution, you have the 2u dx.
cancels with that.
Oh, gotcha. Okay.
It cancels, so that's a good question. Thanks for following. So I have this u squared here, which I expand here, and I get a u squared and a 2u d phi. When I plug this in, the u squared cancels with this u squared, and the other one for the other equation is going to cancel this one, and so you're left with just 2u d phi dx, but there's a 1/2, and that cancels the 2, so we're just left with u d phi dx. Rho I minus omega plus kc plus g times a equals rho prime minus I minus omega plus k c prime plus g a. Okay, so now we're left with this term. So I've just thrown everything into one, I've just replaced the d by dt with omega. And did this with my phi, and my c's turned into the a's, and I'm left just with this. And then we do a little bit of algebra. So then we have, I'm not going to do this algebra because that's boring to watch. So now I've got an equation that has c's and a's in it, and a c prime and an a prime. This came from, let's take a step back. Think about what we did. Started with Euler. Drop in the potential flow. Set them equal to each other at the interface. Deal with the constant of integration. Linearize wherever we can. Do a little bit of algebra. And now the next step is a little bit of algebra. You combining this equation and these two equations, and you're left with rho times minus omega ku plus ku squared plus rho prime omega minus omega plus ku prime squared equals kg rho minus rho prime. This is an intermediate step. We don't have to carry about that. We then solve this for omega.
No, wait. Stop right before the last line.
Last 3 lines. Just
Control Z doesn't work on this board.
No, I know, just the last 3.
Oh, the last one. Stop here.
Yeah.
Okay, cool.
We stopped here.
Yeah, that's good. This is a good place to stop.
Yeah.
Because this still relates, this still has everything that I needed in it. So I'm not gonna write down anything else interesting, I'm just gonna drop down the solution. Now we've done enough to solve this and get the dispersion relationship. So now my dispersion relationship looks like omega over k equals rho u plus rho prime u prime over rho plus rho prime plus or minus the square root of my nodes, g over k times rho minus rho prime over rho plus rho prime minus rho prime u minus u prime squared over rho plus rho prime squared, and the square root of all of that. It's a lot of math. That's a lot of work. It's not super bad once you sit down and focus. You can go through it in an hour.
Yeah. Can I ask you one other thing?
Yeah, Santiago has Anna first, and then I'll.
So, just to like see if I can follow what's going on. So when you do the plug-in step, you're putting everything in. You go back to the equation you have boxed over there. You solve for u. You plug those in for all the u values. But where did all?
No, you solve for the constants. We're getting rid of the constants.
But, like,
So you solve for
I'm trying
C and plug C in here. So you solve this guy for C, you solve this guy for C prime. Plug in your C and your C prime, and then all the A's
for
disappear.
that to get to that equation.
Oh, to get to this equation.
Yes.
Ah, okay.
So,
Oh, yeah,
You
that was
solve-
also my question.
Okay.
yeah, like I'm struggling with seeing what you're plugging into. Then, are you going back to the theta or the phi dot?
No, just right here.
phi one equation?
No, I'm just right at these equations here.
He's doing the derivatives of Fourier.
Yeah, I'm just changing the Fourier, I'm just changing the time derivatives into omega and the space derivatives into k. I'm just plugging in this statement here. I'm plugging in this statement here into my phi 1 and my phi 1 and my c1. So this one gives me a c prime, this one gives me a c prime k, this one gives me a c prime omega, and this one gives me an a. But not a timer omega because there's not a derivative here, just the amplitude. Yeah.
So the partial t is negative I omega, like
Yeah.
the operator.
Yeah.
And partial x is it just ik or is it negative ik?
Plus ik.
Plus ik.
But you can see that from here. It's whatever's in front of the t, so it's minus I omega and plus ik.
Okay.
And that's because you gotta make the line going right. So the reason they come up with a minus sign is so that what you're looking at is a sine wave that's translated.
Could you also explain the last line on this one? Yeah.
Yeah, so I just take this, so I take these two equations,
Yeah.
which are my interface motion equations, solve for C and solve for C prime. And then take this equation, stick in C prime and A. Or no, just plug in C and C prime, and then the A will cancel out. Because you've got a bunch of A's and then you've got an A everywhere and the A's all cancel out. And then you're left with this equation,
Okay.
which is kind of hairy, but it's an intermediate equation that you're getting along the way, and then you solve that for omega. So you take these guys and plug them into here, do a bunch of crap, solve for omega, and you're left with this. Does that make sense? How are we on time? Doing just fine. Okay, does anybody have any other questions on the process that we went to? It's a little bit elaborate, but there's so many good things in here that I want to make sure that we're all on board. Also, it's far not the worst derivation you're going to see in your life. But there's so many, and there's a lot of places where in a textbook or a paper is going to say, we start with this, we linearize and get a dispersion relation, and you're left with here. And they skip all the crap in the middle. So I want to make sure that we're talking about all the steps of all the crap in the middle, because this happens a lot in a lot of different derivations. Okay, so now let's talk about what this tells us. So, okay, any other questions on the derivation? So we're good. Now I'm going to erase the whole derivation and just leave up the dispersion relation.
Okay.
I
Yeah.
just have one question about the Fourier transform a bit.
Yeah.
Are K and omega also supposed to be orthonormal?
They are.
Okay.
They are, I mean, they are the coordinates, so they're independent. So they're independent because they are coordinates, not because they are vectors. So omega and k are the coordinates of the space. The vector is e to the I kx minus omega t. Does that make sense? The basis component is the e to the blah. And then omega and k are the coordinates in that space.
And are omega and k still related by omega is bk?
Omega and k are now related by this.
Okay.
So that's what we're getting at. So the whole thing is getting at the relationship between omega and k. So I wiggle it super fast. How long is the perturbation? And that the system will have to tell you that, because there's nothing natural that will tell you that. Or you have to learn that from the boundary conditions and stuff. Wait, any other questions? I'm going to go. So you'll go through this, and the book goes through all of this, but I might actually, I don't know if this sheet is useful to anybody but me, but it is clearly written out and has everything in it. So I'll probably take a screenshot of this and put it up. Not all of my notes are useful. Some of my notes look like this, which is just a bullet list of things that I have to talk about. Sometimes I actually need the math, so we had this one professor in grad school who he would talk at the board, and he would write something and then erase it, and then write something else and then erase it. And he did for the longest time, and it was the most inscrutable class. And then we were like, could you just Xerox your notes and give them to us? And then he did, and we were like, oh, this is the best. We can understand what's going on. So my notes aren't clear enough to actually make that happen this year. They might be next year. They're getting better as that is always processed. So okay, let's talk about what are some things that we can do with this equation, because it turns out we can do a lot of things. So the very first thing that the book does, and the very first thing that we should do, is say that rho equals large, rho prime equals, okay, let's call it 0, right? What's the density of air relative to the density of water? We're talking about the ocean now, right? It's large. It's a lot larger. It's a factor of 1,000. So let's call rho 1 0. That's okay. A lot of times calling rho 0 ends badly, because nature doesn't, the equations don't really like negative or 0 density. But we can do it here. So if I say that rho prime is 0, and also that u equals 0, u prime is 0, and u equals 0, then we just go through here, and what are we left with? This is 0, this is 0. This term is 0. We're just left with this term. Oh, and we also know that rho is bigger than rho prime. So omega over k, remember this is the phase velocity, so it's omega over k. This is definitional. The phase velocity is omega over k as a definition. And then what omega over k is all that. What we're left with is just equal to g over k times rho minus rho prime over rho plus rho prime. Oh, we're calling rho prime 0 though. G over k. So my phase speed, omega over k, depends on k. So short waves travel faster than long waves in the ocean. No, long waves travel faster than short waves in the ocean. Does that make sense? So if I have the empty ocean in the middle of the ocean with nothing going on, I flick it, waves will travel, and depending on how big big the wavelength is that I will create, it will create waves of various sizes. So deep water waves, which is what we've done here, are dispersive. So remember, I did gravity waves already once, and I got the same answer. So I'm going to go back and real quick recap that. So what we got when we did gravity waves is omega squared equals g k gk, hyperbolic tangent of k times the height of the ocean. And if I do a Taylor series on this, where k is large, hyperbolic tangent goes to 1 if k goes to infinity. So if this goes to 1, then we're left with omega squared is gk, or omega squared over k squared equals g over k, and I get the same thing. If I linearize it the other way with a small k, then I get gk squared, and shallow water waves are not dispersive, because if I linearize this, I linearize tangent, and I get a k times h, and so the right-hand side is gk squared h, so omega squared over k squared is just g times h. So we square root that. So for shallow water waves, they're not dispersive, but deep water waves are. So this gets us the deep water wave equation, dispersion relation. So this is, and actually,
The the only reason why we're not getting the same result for the shallow water is because of the assumption that away like infinity from the interface, we are considering it 0, but in shallow water it would probably bounce back or something.
we assumed everything is 0 at infinity. What you need to do is assume that things go to 0 at a finite value.
Right.
And
Right.
that's what opposes the boundary condition. Yeah.
So how, by looking at the equation,
Which one?
like the one that you wrote, square root gh,
Of this?
the one you just
Oh.
said is the square root gh, and comparing that to square root, like, does that tell you it's non-dispersive because it's height dependent, or
No k.
no k?
There's no k dependence on the right-hand side. So here, this is non-dispersive because every wave, the only thing a wave has is a frequency and a wavelength. Right, the velocity belongs to the medium. So omega over k, neither omega or k appears over here, but there's a k over here. And that's when you get to writing omega over k. If you just write omega, you got to be careful. Omega over k is the important one. Okay, so water, we get that v phase equals g over k, and this is deep water. So yeah, the second thing we can do is Rayleigh-Taylor. So water is rho is bigger than rho prime, and u equals 0. Rayleigh-Taylor is u equals u prime equals 0, and rho is less than rho prime. So that means we start with heavy on the top. Oh, did I put up the picture of the Rayleigh-Taylor? I put up some pictures of Rayleigh-Taylor the other day, didn't I? Bubbles and spikes. I think I forgot to put up the wine glass. I have this really nice wine glass where somebody put something on the top and it's making these fingers. Do any of you guys drink wine? Ever? Occasionally? So if you have a glass of wine and you swirl it around a little bit, you'll get a sheet of wine up the side, and then it will drag down in drips that look a lot like Rayleigh-Taylor. It's a slightly different physics, but it's the same basic idea. Heavy over light doesn't work, it makes fingers. So this makes fingers, wine makes fingers, lots of things makes fingers. So what is this? So what does this dispersion relationship tell us? We get the same dispersion relation now. Omega over k equals this first term goes away and this last term goes away, and we're just left with this middle term is g over k rho minus rho prime over rho prime over rho plus rho prime. So what is the inside here? Rho prime is bigger than rho. The inside here is negative for all values of k. That means that omega is I times gamma, and my xc equals a e to the I omega t. This just turns into a e to the plus or minus gamma t. Actually, don't know if we get the plus. Yeah, I get a plus or minus here. And this is exponential growth, or decay. but it's exponential growth for every wavelength. There are no stable wavelengths for Rayleigh-Taylor. Now, if you introduce a surface tension, that stabilizes things. So then you'll have this plus something that depends on the surface tension. And then not every wavelength is imaginary. Some values of K will give you a positive solution in here, and those will be stable. And the ones that give you a negative solution in here are growing modes, and those will collapse. Yeah.
I've talked about this a lot outside, but like for water, like in the ocean, at different depths, is there also like, would you also have to do this because at different, like deeper you are in the ocean, it's going to be more dense over there, I'm guessing, right? So.
Yeah, here I didn't, for this, we don't care about the bottom of the ocean, really. If you have, oh, sorry, I forgot to put this one up, but I'm gonna, because this video is really, really cool. And I forgot to play it the other day. And this, okay, so this is Rayleigh-Taylor. The video I'm gonna show you is Kelvin Helmholtz. So the answer is, you have to deal with it at an interface. So when you have two different fluids and they're doing different things, they might have the same density and have different velocities, or they might have different densities. So here, do you know why there's turbulence in the air when you're in an airplane?
Because it's an air pocket.
No, I'll show you. How many of you guys have actually been in the not Gulf Ocean where there's actual waves that actually want to take you down? Like the Pacific or the North Atlantic, like the Atlantic side. You know what those waves look like? Now we're just waiting for things to fire up. And then I have to find the thing. So, monohydro lectures.
That's why I'm not good sir. That's why I'm not good sir.
Yeah. This is a building. This is the upper atmosphere. Looks just like the ocean, doesn't it? Okay, so when you're at the edge of the ocean, a wave comes in, and there's a point where the height matters, right? So the wave speed depends on the height. We already got through that, right? So when the bottom comes up close, the wave speed somewhere transitions from a deep water wave to a shallow water wave, and the wave is then traveling faster than the wave speed, and it folds over and it breaks. And that's exactly what's going on here. So we have these waves. These are surface waves, and this particularly coherent video. I have seen the atmosphere trying to do this a couple of times, but I've never sat down with a time-lapse camera for hours on end to actually capture this. But I'm pretty sure it does it all the time. So why is it doing this? Because there's a strata of temperature and density up here. There are layers in the atmosphere of different density and temperatures. So all of this analysis that we're doing works on water waves, but if you're down in the deep ocean and you have a salinity gradient, say you've got, say it gets a lot saltier, all the same physics applies. You'll have waves on the surface of that salt that will travel very slowly, but there will still be waves and they'll still break. So when you're in an airplane, this is what you're going through. You're going through a wave that's breaking in the atmosphere. So there's an atmospheric wave that's folding over and breaking, and that's what turbulence is in an airplane. It's not just isolated pocket of crap. It's doing stuff, just like the ocean. It's kind of awesome. Okay. Do I have anything else that I want to say about videos or movies? Oh, let me pull up the wine glass. Here. Would you just open on the display that I'm on, bubble? So this is a wine glass with like glucose or something in it, and you just carefully put a layer on the top, and eventually it will drop down. Surface tension will hold it there for a second, but then eventually it'll fall down in big fingers. So you can do stunts like this all the time at home, in your kitchen. Okay, that's it for that. I'm gonna turn the lights back on. Where's that button? Oh, how am I doing for time? Oh, I'm doing great for time. Okay, Kelvin-Helmholtz is this. Kelvin-Helmholtz is when you have two different velocities. You can have different densities or the same density. If you formally, if you have the same density, this term goes away, and you're just left with that term. Yeah. Okay. So if I have two fluids, they have different velocities, the densities are the same, what waves are stable and what waves are not stable in that scenario? So if the densities are the same, then this term goes away, and I'm left with something that is negative definite on the inside. So if the fluid densities are the same, then Kelvin-Helmholtz is always unstable. It will always give you a growth mode. And Kelvin-Helmholtz instability, it looks like just a little pocket when it's linear, and that's what we did the math for. But you've seen in some of the videos that I showed that this curls up into big curls in the nonlinear regime when it starts to fail. Every mode will do that because there's no k. Everything is negative for that. See. So we also have Kelvin-Helmholtz. And this is U is not equal to U prime is not equal to 0. And then some waves are dispersive and some waves aren't. So some waves are unstable and some waves are not unstable. So let's look at that for a second. So let's say that U equals 0 for simplicity. Thank you. Let's also say that rho prime equals 0. What does that do for us? So if U equals 0 and rho prime equals 0, then we have omega over k equals, no, U prime equals 0. No, I can't make rho prime equal 0 and U not equal 0. Let's give it a little density. So rho prime, let's say that the top velocity U prime equals 0, and we just have some velocity in the bottom. Then you're left with rho U over rho plus rho prime plus or minus G over K delta rho over average rho, probably positive, minus rho prime U minus U prime squared over rho plus rho prime. So the unstable things are when this part is negative. So that says that G over K times delta rho over the average of rho minus rho prime over, times U minus U prime squared over rho plus rho prime. It's got to be less than 0. And then you can solve this for the criterion of when U and U prime. So some velocities will be unstable, and some velocities will not. So if you go hard enough, you can get it to blow over. So this, you think about just blowing on your coffee when it's too hot. If you blow on it really hard, it goes all over your dashboard. Right? And it's Kelvin-Helmholtz instability breaking your car. This is working on the assumption that everybody's drinking their coffee driving to work. So if you blow really hard, then actually let me flesh this out a little more. If you simplify the algebra, this turns into rho prime u minus u prime squared, it's got to be less than rho squared minus rho prime squared times g over k. So this also depends on wave number. So some wavelengths will be stable and some wavelengths will not be stable. So when you see water on, I don't know, do you ever go to the beach and watch and just look at the soft spot where the water's coming in the right beach and the right times, you'll see these undulating patterns. That's because that's the most unstable mode to Kelvin Helmholtz. And it's just set by the velocity difference, the density difference, and the size of the wave. So all these things play into that. And this also goes back to why honey makes a weird pattern when you swirl water around on top of it, is because of the Kelvin-Helmholtz instability. This is all 1D. You can do Kelvin-Helmholtz in 2D too, and then you'll get weird, funny patterns depending on what you're doing. But it depends on the density of the fluids and the velocity that you're swirling. Okay, the fourth. This one isn't in the book. The Rickmeyer-Meshkov instability is like the Rayleigh-Taylor instability, but it's for when you hit the interface with a shock. I'm only saying that so that you've heard it once. I'm not going to go through the derivation of it. It works a lot like Rayleigh-Taylor. You've got a heavy fluid and a light fluid, and if it's flowing really hard into it, then it'll make fingers that stick in, that penetrate through the fluid. So if you hit a low-density fluid with a high-density fluid, it'll make fingers. Rickmeyer-Meshkov, since it's a shock instability, works both ways. If you hit heavy on light or light on heavy, both are unstable to a finger-like instability. So when you're looking at the literature of Rayleigh-Taylor, the Rickmeyer-Meshkov always shows up because they're very related instabilities. And as we talked about, actually measuring Rayleigh-Taylor in the lab, you got to do something funny. Either you have a thing that slides out and perturbs all your stuff, or you've got to use a rocket or an explosion. So there's often going to be a shock. So Rickmeyer-Meshkov also shows up a lot. You don't necessarily need to know it, but this is so that if you hear it later, you're like, oh yeah, come on. Okay. I have 10 minutes left.
It's 5 minutes behind, yeah.
This clock?
Yeah.
How much time do I have left?
8 minutes.
8 minutes. Okay. Well, let's change gears a little bit. I'm going to talk about something that's not in the book. We're going to talk about gene stability. And this is how stable something is against gravity. So this is star formation 1. So there are 2 time scales that are important for a big cloud of gas that's collapsing. There's the sound crossing time. And so let's say I have a cloud of gas and it has a certain length L and it has some sound speed C sound. How long does it take for a sound wave to cross that cloud? This is really L. L over C. So T equals L over C sound. This is the sound crossing time. Now, if I ignore pressure for a minute and just let gravity take over, then it's going to collapse down to a point. And I'm going to skip a couple of steps, but I'll do them again on Tuesday, and you'll do it for the homework. It's not too painful to sort out, if I have a sphere of gas and there's no pressure, how long it will take to collapse. What you do is you pick a point on the surface. This has a total mass m on the inside, which is equal to rho v. I have a point on the end, and so what do you know if I have a sphere? Let's say it's uniform density. Nah, it doesn't have to be uniform density. but let's say it's uniform density for the sake of argument. It just has to be spherical. What can I say about the gravitational potential that I feel here from all of this stuff? There's one really great simplification I can make. Gauss's law, and then what does that let you do? It lets me replace all this mass in this sphere with all the mass at the origin at a point. Right? This is a nice symmetry of gravitational equations. It's just Gauss's law. So you're sitting here and you say, okay, the gravitational force I'm going to feel, you do some Gauss's law surface like this, and you realize that it doesn't matter where the interface is. You can put it all right at the center. So what we do is we say, I've got a point at the center and a point here, and I know Kepler's laws because I taught Intro to Astro last fall, so I remember them. So what's this going to do? So this is going to orbit on some ellipsis, right? On an ellipse, and the mass is going to be one of the foci. Let's put it over here. Let's make this ellipse have zero eccentricity. Maybe that's infinite now, I forget. So that it's just coming along the ray. It's just going to hit the center. We can still use Kepler's law because it's just gravity, but we just need to tweak the geometry a little bit. I'm going to skip the rest of it and just jump straight to the end. So the free fall time is equal to 3 pi over 32 g rho square root. Now, if you do it this way with Kepler's laws, the 3 pi and the 32 show up for free if you do it right. If you do a proper stability analysis on the self-gravitating Euler equation, you get the same answer. If you wave your hands and try to pull something dimensional out of your shoe, you get basically the same answer. So if I just say I have gravity to the A and density to the B equals a time, remember doing this a couple of days ago, you just write out what all the units are, and you just do the math in the exponents of what are the units on G. It's grams centimeters squared per second cubed, and the units on rho are grams per cubic centimeter. You just do a little bit of algebra, and from that you're left with the free fall time is 1 over G rho. Just units gets you the free fall time. Okay. Now what do we do with that? When I have a cloud of gas in space, there are basically two forces on it. There's the pressure that's keeping it up, and there's gravity that's trying to collapse it. And if the time for a sound wave to cross the cloud is longer than the free fall time, it'll collapse first before the sound wave can get there. And this gives you a Jeans length. So this gives you a certain critical length. So if T cross, which is equal to L over CS, is bigger than T free fall, which is equal to 1 over G rho, then my cloud will collapse because the pressure wave can't stop the density from going up. And I can solve this for the length, and I get L has got to be bigger than C squared over G rho. This is called the Jeans length. I did it really quick and dirty here, and I'm missing some terms. We'll linearize Navier-Stokes again with gravity, and we'll show we get something very similar. But the basic idea is, if I have a little thing, pressure can hold it up. If I have a big thing, gravity's going to pull it down. So how big can it be before gravity wins? This line, C squared over square root of T rho. All right, I think that's all I got for today. Does anybody have any other questions? We'll come back to this next week. There will be a homework due following week. Office hours next Wednesday. I'm pretty sure.
That's a good one. Just got a bunch of settings.
pocket.
Out of class.
So wow.
Oh, wow, that's pretty. App you download?
Yeah, it's just a random app I found on the App Store. So I'm sure you can do actual, like something that looks
Yeah, pretty
similar
real.
to what we're studying.
Yeah, because
but-
all they're doing is solving Navier-Stokes with these terms.
Right, yeah, totally. Just plugging in variables.
That's awesome. I saw one of those that was a browser app that ran in your browser. I was pretty impressed by that. It didn't look as nice as that one. That one looks like it's got better resolution.
Yeah, totally.
Yeah, that's very cool.
It's got like quality and everything, so it looks really nice.
Oh, wow, that is beautiful. Cool.
Hey, Dr. Collins.
Yeah.
Just like a general kind of grad school question.
Uh-huh.